Welcome. Today's notes worksheet is entitled Complex Numbers. We'll begin by developing some ideas with complex numbers, and then we'll do a variety of examples dealing with the operations of complex numbers, and then we'll probably end the lesson solving a few equations where the solution set is in the complex number system. So why don't we go ahead and just take a look at the investigation at the top, get us thinking about what we want to develop, fill in some ideas, and then go ahead and get into our examples. So the investigation says, what type of number is needed to represent the solution set of each equation? And I just have three really basic ones right here dealing with different representations of numbers. And so as I look at 2x equals 1, the first type of number that I would think about is a counting number, 1, 2, 3, 4, etc. And if you look at this equation, there is no counting number that would make this equation true. So we need to expand our representation of numbers to solve an equation of this sort. And as a result, we need some type of fraction, which it happens to be called a rational number. So what type of number is needed to solve that type of equation? Well, we would need a rational number to do that, something beyond the counting numbers. All right. Now, everyone, we move over here, of course. And if I asked you to solve this equation right here, you would, of course, square root. And by undoing this square, you would get the square root of 2. But you would, of course, remember to put the plus or minus out in front to take both roots. But the bottom line is, there is no counting number that makes this equation true. There is no rational number that makes this equation true. And so as a result, we need a new type of number to make this equation true. And so we have the development of what are called irrational numbers. Okay, and we know all about those. Won't go into that in too much detail. Now we go over to this one right here. And by the way, everybody, just if you remember from way back when, the real number system is made up of all the rational numbers and irrational numbers. So this set of numbers and this set of numbers compile what we would call real numbers. Now we go to the last one, of course, x squared equals -1. You would, of course, do the same thing. You would undo the square by square rooting both sides. And you see, of course, trying to take the square root of -1, is there any rational number that would make that equation true? No. Is there any irrational number that would make that equation true? No. And as a result, there are no real numbers that would make this equation true. There's no way to get a real number as the square root of -1. And so, of course, without a whole lot of issue here, guys, we introduce the idea of an imaginary number in order to satisfy the requirements of that equation right there. Okay, and the imaginary number system is all really based on the foundation of the imaginary unit. And so I'm sure you've seen this before, and that is denoted by I. And I is represented or defined as the square root of -1. So guys, if you can box that piece up, of course, that would be ideal. And now we have a way to represent the square root of a negative. And in this case right here, that would satisfy that equation. Let's see what we have on your paper here. So I, of course, is equal to the square root of -1. Now we can deal with the square roots of negatives. And then just on your paper it says which means, and this is what I was thinking. So we're going to see this throughout this entire notes worksheet. So let's get this in play. So if I is equal to the square root of -1, I guess I would ask you this and see if you remember, what is I squared equivalent to? And I squared, of course, if you square both sides, square that and square that, well, squaring the square root of -1, of course, just gives you -1. And so we already have a connection here between our imaginary unit and the real number system. We just have to square the imaginary unit. So I squared, now we're back to the real numbers, in this case as -1. Keep that in mind if you would, as we'll see that, as I said, when we do some operations. All righty, well, let's move on to the next piece. So all numbers, all of our real numbers and imaginary numbers, fall under the umbrella of what is called a complex number. And so that says the number system that results from introducing the number I. And you probably have seen this version before, so we're going to look at the standard form of a complex number, and it would be this right here, kind of made up of the two parts, the real part and the imaginary part. And that's what makes up a full, comprehensive, complex number. And so if you remember correctly, the a part of this complex number is the real part of it. Let's jot that in there, of course. The b, of course, represents sort of the imaginary part. And I, of course, would be the imaginary unit. All right, very good. And so we can kind of talk about what types of numbers we get when a and b change. So we'll just do a little piece of that. And as I said, a good portion of today's lesson is to just deal with operations on this complex number. So it says, what type of number do we get if b is 0? So think about that for a second, just covering this part up because b would be 0. And of course, if b is 0, you're only left with the a part right here. And that would mean you're just getting a real number. And you do not have to write this on your paper, of course, but obviously any real number can be written as a full complex number. You know, if I have the number 3, just theoretically, that really is 3 plus 0i. Now, it doesn't seem necessary to write it like this, but there's actually some mathematics where that is desired to kind of write it like this, and potentially those going on to Pre-Calc 2, you kind of might see that in action. All right, so Pre-Calc 2, that is heavy on the trigonometry, comes back a little bit to complex numbers towards the end. There's an interesting connection there. All right, onward here to this next piece. It says, what type of number do we get when a is 0? So that would be covering up this part of the complex number. And you would just get the bi part, of course, and this is what we would call a pure imaginary number. So if you can jot that in, of course, that would be great. And if we have a not being 0 or b not being 0, and we have this complex number right here, it is considered an imaginary number. It's just when this is 0 and we just get this piece, it's what's called a pure imaginary number. So I know it might be a little weird to make the distinction between an imaginary number, which would be really this whole thing, neither one really being 0, and a pure imaginary number where we're just really focused in on this piece. This part is 0. So anyway, take a look at that if you would. And then let's get busy with some operations. We will start out nice and easy, of course, and then kind of build our way up. So let's see what we can do. I've got 2 operations taken care of right off the bat on your paper here, and it just says adding and subtracting, and then just left a little blank for me to put my 2 cents in. And I guess I would just characterize it as when you add and subtract complex numbers, basically everyone, you're just combining like terms. And you've had a lot of experience with that over the years. And so we're just going to combine the real parts together, we're going to combine the imaginary parts together, and that's really all that's required when you're performing operations in the complex number system with addition and subtraction. So in this case, I have 8 plus 4i as one complex number, and then I'm going to take away 10 minus 2i as a secondary complex number. And again, in terms of subtraction here, I just need to work with the real parts and the imaginary parts. So I have 8 units, I'm taking away 10, so negative 2 in terms of the real part of our complex number. I have 4i, I take away negative 2i, subtracting a negative is just like adding a positive, so 4i minus negative 2i should be 6i. And that's really all that's required right there. There is some visualization with complex numbers that you'll see, again, if you decide to take Pre-Calc 2. Again, perform quite a bit of operations, and you see it in a little more of a visual way. But you need some trigonometry to have the background to pull that stuff off. Okay, so adding and subtracting, really not too much to talk about. I pretty much gloss over that and move on to the next operation. And so as you can see, the next operation will be multiplying our complex numbers. And so what I boiled it down to is either you're going to distribute or you're going to FOIL, just depending on the nature of the complex numbers. FOIL really is just a fancy way to talk about distributing. So really they are the same. And so let's go ahead and do a couple examples together. You can always just do them on your own and fast forward and see if you get them right. You know, totally up to you. So what I have, of course, is this pure imaginary number right here, negative 3i, times this imaginary number right here, this complex number 5 plus I. And so, really it's just a matter of distributing it in. Something like that would do. And you'll see a couple things emerge, which I'm sure you've seen before. So I have negative 3I times 5, and should give us negative 15I. And negative 3 times I, so negative 3I times I, should give us negative 3I squared. And that looks good. It's a great first step right there. No issues whatsoever. The one thing that I would have us do and ask you to do very lightly on your paper is to circle the I squared, because we're not quite done just yet. And if you look above, you can see that this actually translates into something nicely, so we can simplify this a little further. And just because this is the first time around, I'm going to take it all the way through, but basically, remember, I squared translates right back into the real number system as negative 1. And so as a result, I have this piece right here is negative 3 times negative 1, which is positive 3. So as a matter of fact, this gives us the real part of our complex number answer. So I have a positive 3 and minus 15I. Now theoretically, the order doesn't matter in which you write these. Typically, you'll see me write it as A plus BI, just keeping it in that standard form, of course. So shoot for that if you can. So I'll box that one up, and just kind of thinking about it, I'll box that previous one up, and then we'll move forward on to the next. All right, great. So now I have two imaginary numbers, 2 plus 5I and 3 minus 4I there. And so this would fall under the category of foiling. So F-O-I-L, and something like this. You don't have to draw in the arrows if you don't want, but that's essentially what happens. So I'll go ahead and run these through. If you want to go ahead and do it as well before me, that would be great. So 2 times 3 is 6. Let's get that going. Outside, 2 times negative 4I is negative 8I. So 2 out of the 4 taken care of. Then I revert back to the inside here. 5I times 3 is definitely 15I. And then the last is what we'll be a little careful on. I have 5I times negative 4I. So definitely a negative 20, and an I squared on that should do. Just be careful on that piece. I times I is going to give us that I squared right there. Everything's looking good. I'm going to take this in a couple steps. If you can do it in one, more power to you. But basically, you can see, of course, that same deal. This is negative 1. I squared is negative 1, so this reverts to just a real number. Negative 20 times negative 1 is positive 20. And now, of course, we just combine the things that can go together. So in terms of the real part, the 6 and the 20 will get me to 26. And in terms of the imaginary part here, it looks like I've got the negative 8I plus the 15I. And I like that piece right there. All right, so just operation dealing with multiplication. Just working through. Should always get a complex number as an answer, and looking for the real part and imaginary part with that I. All right, let's go on to the next piece. So if we're going to do our fourth operation, already actually in this lesson, we need to set up a couple ideas first. So division is done a little differently than what you would think. So what we're going to do is employ the use of what is called a conjugate. So I've got just some algebraic jargon right here. Let's see if I can translate it a little bit for us. So it says conjugates of a complex number. So guys, here's your complex number. You'll see this come up with these complex numbers, the z. So z is going to be our complex number. There it is, guys, in standard form, a plus bi. Then the conjugate, very simply in terms of notation, is this z bar right here. So that just means we're dealing with the conjugate. And again, the bar over our complex number is the conjugate. And this is how the conjugate is defined. So if our complex number is a plus bi, well, very simply, the conjugate is a minus bi. And so what I put here is just to break it down in layman's terms, and here's how I would say it. And you can hopefully analyze it from the algebra there. Basically, a conjugate has the same real part and the opposite imaginary part. And conjugates are used in a few different contexts with algebra. It's a nice technique to do some operations and some simplification. So let me just make sure I have that. There we go. Same real part, opposite imaginary part. All right, so example 3 should probably take us literally about 10 seconds total here. It just says find the conjugate. So same real part, opposite imaginary part. So the conjugate of 4 plus I, very simply everyone, is 4 minus I. Same real part, opposite imaginary part. Letter B, negative 3 minus 2I. And so negative 3 and then plus 2I. And you'll see the rationale for using these conjugates in just a couple minutes here. Give it a moment to develop if you would. Now for a pure imaginary number like this, we actually probably won't utilize the conjugate, but it does have a conjugate, and so I guess I would argue that it's just probably going to be 4i. And that's pretty much it. Just kind of get used to that piece. And then you'll see this in action. Really, it kind of boils down to the conclusion that can be drawn from this particular piece right here. So it says on your paper, what type of number is produced when multiplying two conjugates? So what if I did have something like this? And think of any two numbers that you can put in for A and B. What if I asked you to multiply those two conjugates together? What type of number would you end up getting? You would, of course, FOIL. And you would do A times A, of course, and get that. And you would do the outside and the inside. And those are the two pieces that give us the imaginary part of the complex number. What happens when you do that? Outside, inside. Well, if you notice, they're the exact same term, except one is negative and the other one is positive. And so as a result, the pieces that would give us the imaginary part cancel out. And then when you do the back, of course, you get an I times I, which is I squared, so that's going to be back in the real number system. And so you only get the real number parts. And when you combine them together, you just get a real number. And that's how we're going to play it out. Now, you're going to be doing this momentarily, so just want you to get comfortable with it. You can always just FOIL these out when there are numbers in place, and you'll see this in action. But just wondering if you can come up with a little shortcut yourself. What do you actually get algebraically when you multiply those two together? And as a result, if you do this, take a look. You FOIL, and you get A times A, which is A squared. We said the outside and inside definitely cancel, and I'll stick with that. And then what would happen on the back? That's kind of interesting. Look at the back. You get B squared and I squared, and positive and negative. So really you get minus B squared I squared. Think about that for a sec. Minus B squared I squared. But as we all know, I squared is negative 1. So minus B squared I squared changes the sign, and you end up just getting plus B squared. Now again, it's just a nice little shortcut there. I'll maybe make reference to this as we go through. But bottom line is, when you multiply those together, you do get a real number. All right, well, let's go get our fourth operation here. It's primarily division, but the idea of a reciprocal also falls in line here, so I'll go ahead and put that in place as well. Okay, so our goal with division is to do a little algebraic trickery, I guess. The idea is we're going to eliminate the I in the denominator. And there is actually some context for doing this that you've seen before. So the idea behind this is not dramatically new. But we're going to eliminate the I in the denominator. And the way we're going to do that, guys, is we're going to either use I for a pure imaginary number. And jot this in if you get an opportunity, and then you'll see kind of the rationale for doing that. So pure imaginary number. And we're going to use the conjugate, there it is, right there. That's why we kind of went through that piece, for a full complex number. Or really it's called an imaginary number, but I'll try to distinguish it a little better. So I'll just write it like that. Okay. So again, if this, you're like, oh, wait a minute, I'm not seeing why we would do this and why we would do this, give it a moment, let it develop. And then now you'll have this as a reference for it. All right, so let's go see how this is going to play out. Example 4 will be the reciprocal version, and example 5 will be just the division operation. But both really are the same. So let's do example 4 first. It says, find the reciprocal of 2 plus 5i. Now reciprocal, just remember, I've seen this over the years, on a reciprocal, guys, we don't change the sign. We just flip the number. And don't write this on your paper because I'm going to erase it momentarily. Remember, 2 plus 5i is really written like that, just over 1, of course. So the reciprocal is literally just flipping the number. Just keep that in mind. We don't change the sign. A reciprocal, we just flip the number. Okay, so that's what we're going to do, of course. And then notice our directions there. This is the reciprocal. But what we want to do is write the number in standard form. We want to write it in true a plus bi form. And the dilemma that I see, the way we wrote this right here, is that I have I in the denominator of a fraction. That, of course, is not standard form. So the way we have to play this out is to eliminate that I in the denominator. And that's what I wrote above, just in those blanks there. So rather than talking about this as like a division algorithm, how many times does 2 plus 5i divide into 1, which is pretty much what it's saying, what we're going to do is tweak the number to get rid of the I. And the way we do that with this complex number right here is multiply by the conjugate. To eliminate I in the denominator and change it from a complex number to really just a nice real number, we multiply by the conjugate. Now it's a fraction, everybody, of course. What I do to one part of a fraction, I must obviously do to the other. And so we just get that piece right there. So again, a little algebraic technique or a little algebraic trick, whatever you want to call it, to write the number in its proper form. Now I'm going to do the top here first because that seems nice and easy for me. So the top just basically says 1 times 2 minus 5i. And, you know, that shouldn't scare me too much. That should just be 2 minus 5i. All right, now here's what I would love for you to pause the video for just a moment, and can you FOIL the bottom? So 2 conjugates multiplied together. What type of number should we get? Definitely a real number. See it? All righty, guys. Well, if I do this, 2 times 2 is 4. I'm just going to write this below just because I'm thinking about it. Remember, the outside and inside cancel. And then we get minus 25, 5 times 5, I squared. And remember, I squared is negative 1. So instead of minus 25I squared, it becomes plus 25. And there's your 29 right there. That's the key. Make sure you do see that piece before moving on. And remember what I said earlier, that the quick trick, if you want to employ it, is if you know A and B, A is 2, B is 5, 2 squared plus 5 squared. 2 squared is 4, 5 squared is 25, 4 and 25 make 29. Now, if you left your answer like this, I can live with it. We're always kind of shooting for you know, just perfection, so to speak. I would split this up and really see it in all its glory as a complex number, an A, and then plus BI, so kind of having the real part and the imaginary part separated. You know, there is some rationale for doing something like that, especially as you dive deeper into complex numbers. But, you know, again, if you left it like this, it's fine. I can live with it. But I'd encourage you to try to shoot for something along these lines right here in your representation of your answer. All right, so this is just a common denominator, so it goes under the 2, and it goes under, we could just consider it the 5. Okay, if you have a question on how to write those, please call me over at any time. So conjugate, guys, nice work there just to get rid of that I in that complex number. Now, dealing with a pure imaginary number is slightly different. I want to know, I want to determine how many times does 4i divide into 2 minus 3i. But again, I'm not setting up some type of division algorithm. I just want to get rid of the I. If I can do that, I've really actually performed the operation. And so as a result here, I'm going to multiply But in this case, I actually don't have to multiply by the full conjugate. So if my goal is to just eliminate the I, as it says, just use I itself. If you use the conjugate here, you would eventually end up with the same thing. But because it's a pure imaginary number, what I'm going to do is just multiply it by I to revert it back to the real number system. Because of course, guys, this piece, what is I times I? I squared. And it's done its job. So in this case, unlike the previous one, it wouldn't have worked in the previous one, by the way, we can just multiply by I. All right, so let's do the denominator first, as I talked about that, and then we'll clean up the numerator. So 4I times I, well, again, I squared, and I squared is negative 1, so 4 times negative 1 is negative 4. Beautiful. Now this distributes into this right here, so distributed into the 2, distributed into the negative 3I, I should say. And 2 times I is 2I. And let's see, I times negative 3I is negative 3I squared. Negative 3I squared, everybody, should be positive 3. Again, make sure you see that piece. If you need to write more things out as you go through the process, please do so. If I shortchanged you a little bit, my apologies on that. Now again, if you left it like that, it's not wrong. I think it really has a little work to be done to really make it satisfactory, in my opinion. So real part and imaginary part. So let's do it. Hey guys, real part right here. Real number on top divided by the real number down below. Positive 3 over negative 4. And positive 3 over negative 4 is really just negative 3/4. Imaginary part with the I attached to it. So I have a positive 2 over negative 4, and I can deal with a positive 2 over negative 4. 2 over 4 happens to be 1/2. And then, of course, times your imaginary unit is I. And again, this is what I'd encourage you to look at this level. Maybe Algebra 2, you probably left it like this, and just, again, looking for maybe something like that right there, if you can. So there is division. A couple different variations on it. Look at those examples, see if it clicks. All right, new operation, guys. Let's go dealing with just powers of the imaginary unit. A couple we've already seen, and some patterns to develop, some really fascinating patterns that deal with the value of I when you raise it to a particular power. So let's see if we can pull this piece off, and then we'll start to round it out. All right, so guys, I to the first, of course, is just I. No question about that. I squared, we already developed, is negative 1. Now let's go further. Let's see. Just using some exponential properties to get this going. So everyone, I cubed is really I squared times negative 1. I squared times I to the first. I squared, everybody, is what? Negative 1. I to the first is I. And so when I do this operation right here, having broken down I to the third, negative 1 times I is negative 1I. There you go. Okay, nice. How about I to the fourth? Look at what I developed here. I to the fourth is really just I squared times I squared, huh? And I squared is negative 1. Oh, wait a minute. I squared is also negative 1 again. And negative 1 times negative 1 is 1. All right. Now, there is a reason that you see these blanks laid out the way they are. So I would love for you to pause the video for, about 60 seconds, give or take, and see if you can figure out these remaining powers of I. Well, let's see how you did if you pulled it off here. Now remember, I to the fourth, we already did this, and this is my breakdown. You could break these down in so many different ways. This is just how I did it on your sheet. But remember, I to the fourth is just 1 now, right? So you've got 1 times I to the first, and so this is just I to the first, I. Same here. I to the fourth, which is 1 times I squared, 1 times negative 1 is negative 1. And what you would see if you did this all the way through, so we can expedite this along, is that the exact same pattern repeats. It goes I then negative 1, then negative I, and then 1. And if I was to continue this pattern, I to the 13th and 14th and 15th and 16th, it would be that same cycle of 4. And that's exactly the piece that we'll look at this last look here. So, conclusion. Hope you saw that piece, how it is broken down. But very simply, the powers of I, it's kind of fascinating how these patterns work out. Powers of I repeat in cycles of 4. So our job, of course, is just to see where in the cycle of 4 it is. So I can give you any power of I as long as you know which row it's in out of this cycle, you've got it. Top row, it's I. Second row, negative 1. Third row, negative I. Fourth row, positive 1. And so the way to kind of pull this off numerically is to just talk about doing a little division on the exponent. And because it works in cycles of 4, we're going to divide it by 4 and determine what's left over. And so when we determine what's left over, we see where we are in our next cycle of 4. So here's what it looks like. If the remainder is 1, this would be the first row. This would be 1 is left over. Then the power of I is equal to I. So that would be top row. This means if the remainder is 1 after dividing by 4, well, we're 1 into our next cycle. We're in the top row. If the remainder is 2, then of course, guys, 2, second row, and the second row is negative 1. If the remainder is 3, then we're 3 into our next cycle, and that would be the third one down, which is negative I. And last but not least, if the remainder is 0, this would be the same as saying the remainder is 4, although we wouldn't say it that way. Then we're in the bottom row, and of course, it's 1 right there. So when we do example 6 here, for any of these powers, the idea is just to see where we are in our cycle of 4. Are we top, second, third, or the bottom? And so let's go ahead and do a couple of these together, and then would love for you to do 1 or 2 on your own. But if I want to know where I to the 20th, what it would simplify to, I would just have to envision where it is if I continue this pattern. Again, 13, 14, 15, 16, et cetera, et cetera, et cetera. Now 20 you can probably picture pretty easily, but let me do the math just so we can back that up. So the way I would pull it off just mathematically is just take the exponent and divide by 4. And of course, it goes in 5 times. And that really just talks about how many cycles into it we are. But basically what I'm looking for is the remainder. And of course, we all know that the remainder is 0. And so what that means for us, essentially, if the remainder is 0, then our exponent is evenly divisible by 4. And that would put us in our pattern here in the bottom row. These are all the numbers that are divisible by 4. And so as a result, if you were to kind of track this out here, we would be in the bottom row of our pattern. So I to the 20th is just 1. And that's how it would play out. Let's go try the next one. So 20 I think we could have seen. It really just goes 13, 14, 15, 16, 17, 18, 19, 20. Bottom row. Now I to the 53rd, again, rather than having to count it all out there, so let's just do 53 divided by 4. And you grab your calculator and, let's interpret. We've got 53 divided by 4, which would be 13. So it's kind of 13 cycles, but it should say 13.25. So what that means, of course, is it goes in 13 times with 1 out of the 4 remaining. So 0.25, of course, is 1 over 4. And so what this means, of course, is that is your remainder right here out of the 4. That is where we would be in our new cycle of 4. And if we are a remainder of 1 in our cycle of 4, that means we're at the top in our cycle of 4. Sorry for the redundancy there. And if we're at the top, hey guys, I to the 53rd happens to be I. Very cool. All right, let's go do the next piece. So I take 79 and I divide by 4. And please, again, feel free to pause or fast forward a little bit if you understand exactly what's going on here. If not, again, bear with it, see if it works these last few examples. So 79 divided by 4, in this case should be 19.75 if you brought your calculator up there. All right, which means 19 times and 3 out of the 4 remaining left over. So there's your remainder right there. There's your 3. So we are 3 into our new cycle. And if we are 3 down in our new cycle, again, 1, 2, 3. Now hopefully you're really able to picture this piece, negative I. Awesome. Letter D, guys, here we go. I to the 46th. Where are we in our cycle? Well, in this case, if you were to do this on the calculator, you'd actually get 11.5. So what that means is 11, and how many out of 4 would 0.5 be? Well, it would be 2 out of 4. So that's basically what we're saying. When we do that operation right there, there is your remainder, and that means we are the second down in our cycle if you counted it out there. And I to the 46th, of course, is negative 1. Very, very cool. Let's do just letter E, kind of bring this last piece, and then we'll hit the quadratics to wrap it on up. So how do I deal with a negative exponent? Well, it looks like I started to give it away already, writing before I was saying it, but that's all right. So how do we deal with a negative exponent? Well, we make it positive by bringing it down to the denominator of the fraction there. So I to the negative 27th, of course, is the same as 1 over I to the 27th. Now, I will just move this along, of course, just a little bit. If I made you simplify I to the 27th, just like I did all these others, what we would find is 27 would be the third one down in the cycle, if you counted it out there. And so as a result, it would be negative I. Now, is this an answer that I would accept if we're talking about complex numbers in standard form? No, absolutely not. So let's slow it down for a sec and figure out how we're going to work this out. No I in the denominator, guys, so how am I going to clear that out? Well, if you remember from above, I multiply the bottom by I, and that should change it back to a real number. Because it's a fraction, anything I do to the denominator, have to do to the numerator. So it'd be great for you to clean this up here. What is negative I times I? Well, this would be negative I squared, and negative I squared is really just the opposite of negative 1, which is just 1. And then on the top, 1 times I is I. And so as a result, you just get I. Very cool. All right, so negative exponent there. Just be careful on that piece. There are some patterns with the negative exponents. I will let you kind of look it through, maybe see if you can find a couple shortcuts with it. All right. Doing pretty good on time here. There are a couple more things to accomplish. So take a deep breath, and let's see if we can refocus just for the last two pieces. Trying to get a lot of complex number examples and ideas into one lesson here. So even though it's a little lengthy, see if you can stay with it, please. All right, here we go. So one of the ideas behind dealing with I is that now we can actually work with square roots of a negative number. And so what we're going to do is basically this. We're going to use the product property. Let me just make sure I write that correctly for us. So use the product property, and that's how you simplified square roots in all your previous math courses. So use the product property to write I as a factor. All right, beautiful. So I'll show you how this works momentarily. Example 7 just now talks about simplifying square roots of a negative. And remember, obviously, the real number system is not able to accommodate such a simplification. But now that we've expanded our representation of numbers beyond the real number system, this is something that we can work with. And so bottom line here is the product property works something like this. Any two numbers multiplying together to give us negative 25 can be written under the roots. And so as a result, I being the square root of negative 1 we take that out as a factor. And now this is not too bad because the square root of 25 is just 5. And the square root of negative 1 is just I. And so we talk about this as the square root of negative 25 being 5i. Let's just work through letters B and C as well, just using the same idea. And if you have other ways to simplify square roots, please go ahead and do that. But I would think about the numbers that go into 24, specifically the perfect square that goes into 24, which happens to be 4. So in terms of just the number 24, 4 times 6 works great here. But because it's negative, I want to go ahead and write I as a factor, so taking out that square root of negative 1 from this number right up here. And so I get 2, square root of 4 is 2, square root of 6, and the square root of negative 1 is I. And that would be a great answer right there. Just in terms of writing these, just FYI, sometimes you'll see it like this. And again, it's all multiplication, so it's really not that big of a deal how you write it. So either of these would be satisfactory. You see both of them for sure. So either 2 root 6i or 2i root 6. Same deal. The one thing you do have to be careful of, just over the years I've seen some strange things. I've seen students kind of try to put the I underneath like that. And just maybe on your paper, just write that that would be incorrect. All right, let's do letter C. So square root of negative 80. This is a good hard one here. Again, if you have good number sense, you probably can see the perfect square that goes into 80. If you need to find another method, use another method. But just to move this along a little bit for you, 16 I think is the largest perfect square that goes in. So I'm thinking we're going to look at something like that right there. So square root of 16 is 4. Square root of 5 can't be touched. Square root of negative 1 is I. And that's looking great. So again, however you play that out there on these, that looks good. 3 good answers. So pulling out I as a factor, that's the way we're going to work with square roots of negatives. Which brings us finally here, guys, to the last piece. And we've dealt with quadratic equations before. All our solutions were in the real number system. Now let's go ahead and see if we can develop those same ideas, but see our solution sets being in the complex number system. So let's go for it. Different methods to solve a quadratic, everyone. There's factoring, there's undoing a square, there's completing the square, there's quadratic formula. I'll pick and choose here, and then let's solve these 3. So I'm thinking in this case, because there's no middle term, this is a great equation to just bring over the 36 and undo the square in order to get the variable by itself. And so as a result, I'm going to go ahead and do that right there. Undo the square on the left, and of course you get x. Now remember, this is an equation where I am undoing a square. And so as a result, as you have seen before in your math classes, we do need to take both roots of negative 36. And so I take the positive of it, and I also take the negative of it. And what is the square root of negative 36? Think about what we did up here. Well, the square root of 36 is 6. But because it's square root of negative 36, we have to, of course, sorry about that. We have to, of course, take out I as a factor. And so we get plus or minus 6i. And there you have it, 2 answers. If I took 6i and squared it, you get negative 36. Add the 36, you get 0. If I did negative 6i and square it, you get negative 36. Add the 36, you get 0. Cool. Letter B. This does not factor. And I could not undo the square. I'm partial to completing the square, so that is exactly what I'm going to do. Let's get some good background on this. You're going to do a lot of completing the square in this curriculum. So let's check this out. So x squared plus 2x, get the blank going. The 2 moves over, becomes negative, and get a blank going. Beautiful. What do I want to add right here in order to make a perfect square trinomial? I'm thinking a plus 1 would do. Balance it off, of course, everybody. Plus 1 right over there. The whole reason for completing the square is because it factors so nicely, changing the form without changing its value. That should be x plus 1 squared. And of course, negative 2 plus 1 is negative 1. Now I'm ready to undo the square, just like I did on the last problem. It's a little more complex, but not too bad. Those cancel out right there, and I just get x plus 1. Here's where you come in, everybody. What would the right-hand side look like? Because I undid the square right there, guys, of course, it's plus or minus. And what is the square root of negative 1? Hey, remember, that's how we started this lesson. Just I. So we got plus or minus I right there. Shall I go ahead and subtract 1 on both sides? Yeah, and you don't have to write that in there, just hoping you see it. Typically, you see the negative 1 come first, the plus or minus in the middle there, and negative 1 plus or minus I. And interestingly enough, if you put negative 1 plus I in for x, it works. Those operations would give you 0. Negative 1 minus I, same darn thing. Cool. Last one. All right, you ready for this one? This is as hard as it gets. So bear down on this one if you can. Let's pull it off. I'm going to complete the square, and as we've talked about, really we want a single x squared out in front. Let's get that x right there. 4/3 equals 0. So first step, divide everything by 3, clean that out a little bit. Now we're going to get some fractions, but we'll have to deal. I have x squared minus 2x, 2/3 x, give me a blank, and you get negative 4/3 on the other side as it moves over, and give me a blank. All right, it would be great if you have the wherewithal. Can you see what goes in that blank right there? Take half of this, and of course, square it. Well, half of that, I'm just going to work off to the side. Half of negative 2/3 is really negative 2/6, sort of half, just another 2 down on the denominator there. Negative 2/6 is really negative 1/3, and when you square negative 1/3, I'm thinking you get 1/9. And so I get 1/9 and 1/9 right there. All right, now I think it rolls. Here we go. The whole reason, of course, is it should factor to something times itself. X times x would give us the x squared. 1/3 times 1/3 would give us 1/9. And they have to combine in the middle to negative 2/3. And so it has to be a minus right in there. Very, very cool. Now the other side of the puzzle here is this piece. I've got negative 4/3 and 1/9. Negative 4/3. I think we want to get as a common denominator here, which looks to be 9. I'm seeing this as negative 12/9 and 1/9. And negative 12/9 plus 1/9 is negative 11/9. All right. Ugly numbers, but hey, it is what it is. Let's see. Square root, square root. I get x minus 1/3 plus or minus. Now look at this one, everyone. See if you're really putting it together. Square root of 9 down on the bottom, just 3. Square root of negative 11, not much I can do there, but I can deal with it. Square root of a negative, let's pull out I. So square root of 11 times I. And guys, would you all, of course, to get the variable by itself, would you, of course, add 1/3 to both sides? And when you add 1/3, do you see, of course, these have the same denominator? I'm seeing a great answer emerge. When that moves over, it becomes positive. So 1 plus I root 11 and all over 3. See a lot of quadratic solution sets looking like that. It's a winner. Is it a clean, beautiful answer? No, but it's as legitimate as any other. Hey, again, we spent a lot of time going through a variety of things with complex numbers. This was a long one. Chances are you broke it up into a couple different parts there, and I hope that's the case. So get a little practice on it, see what you can do, and check in with me. See if you're working okay with these complex numbers. Thanks for listening to the lesson.